As you can see from the title of my presentation, it has nothing to do with bacteria or microbial proteins, which are the main theme running through the other presentations in this session. But I still think we hold some things in common, and we try to convert CO2 into useful products. And also, if you're familiar with the concept of microbial electrosynthesis, then you will find the systems quite similar, only that we use inorganic catalysts to drive the conversion of CO2 rather than microbes. So you're all familiar with the problem of rising greenhouse gas emissions. And to make the process of electrochemical reduction of CO2 truly sustainable, that would largely depend on the energy mix we employ to drive the reaction, whether it's solar, wind energy, or nuclear, or whether it's gas, besides the other reaction metrics and process scheme that would affect the cost of the process. But there are and there will be incentives for companies to certainly the ones that produce CO2 at high concentrations to recycle that gas rather than to emit it to the atmosphere and pay the expected tax in the future. So with the electrochemical reduction of CO2, we can make several products, largely depending on the catalyst. And in this talk, I would focus on the evolution of carbon monoxide and of ethylene and ethanol and multi-carbon products over copper-based electrodes. So whether we form a CO or multi-carbon products at the catalyst surface largely depends on the binding energy of CO to the catalyst. And we see that copper is pretty unique in that regard because it has an intermediate binding energy to CO, which allows it to convert it further to ethylene, methane, ethanol, and other products, while gold, silver, and metal nitrogen doped carbons have a more endothermic binding energy towards CO and therefore desorb it as CO gas. So in this configuration, we can have a solid electrode, solid metal electrode, or an inert conductive electrode where we deposit copper nanoparticles or carbons. And they will be in contact with an aqueous electrolyte containing dissolved CO2, bicarbonate, depending on pH carbonate, and also hydroxide ions that will complete the circuit. And also we will have an anion exchange membrane to prevent product crossover to the anode, where we will oxidize water to oxygen gas, for example. Now, in the bifunctional catalyst concept, we would like to combine those two functionalities, the CO evolving one and the CO reducing or CO2 reducing one to multi-carbon products in one bifunctional catalytic entity. And we can explain this concept graphically by plotting the selectivity of the reaction as a function of electrode potential, which is in fact like the driving force of the reaction or what drives the kinetics of the reaction. And we can see here that the nickel nitrogen doped carbon, which is the CO evolving function, forms CO at high selectivities at moderate overpotentials, while copper nanoparticles, when deposited on an inert conductive substrate or in combination with carbon black, catalyze the formation of ethylene and methane at higher overpotentials. Now, of course, we would like to achieve a high selectivity towards one product because that will increase the energy efficiency, and we would also like to increase the selectivity of the carrier, in this case the metal nitrogen doped carbon, as high as possible. In a later stage, we would also like to reduce the overpotential, also to increase the energy efficiency, as you can see in the term here, and also reduce the power consumption of the cell. But in this talk, I will focus only on the high overpotential region. Now, we also have to discern what we call the real catalyst selectivity or real selectivity of the carrier here, and what we observe or what we measure at the outlet of the reactor. And of course, we would like to have the selectivity of the carrier as high as possible and the observed one as low as possible, so that the majority of the CO evolved from the carrier would then continue and cross over to the copper functionality and will be reduced there to multi-carbon products. So here's an example of such a bifunctional catalyst we synthesized. So we synthesized copper nanoparticles via an ammonia-driven deposition precipitation method. And we deposit those particles on a nickel-nitrogen doped carbon. It is doped with these atoms to make it more selective towards CO, because normal carbon black or active carbon is inert to the reaction and form largely hydrogen gas, which is the byproduct of the reaction. And by doing this synthesis, we can obtain 8 to 8% of copper on the doped support. And the proof for the presence of nickel, nitrogen, and copper on the surface, you can see here in the TEM images that I depict in this slide. And here are the first results of that catalyst when we measured it under the same conditions as in the base scenario. And again, you see here the selectivity as a function of overpotential and selectivity towards ethylene of CO of the bifunctional catalyst. And you can see here that the selectivity of CO of the bifunctional catalyst is higher than in the base scenario. But when we increase the overpotential, it decreases as well. And at the same time, we see an increase of the selectivity towards ethylene, which might suggest a synergistic action between the two functionalities. But at the same time, we had some issues with the synthesis of this catalyst, and we had some issues with copper nickel alloying during the synthesis. And also in the configuration, cell configuration we used, we obtained only low current densities because of CO2 depletion near the catalyst surface, probably because of the higher pH at the electrode surface and the low solubility of CO2 under these conditions. So to tackle those two problems, we went on to synthesize copper nanoparticles in a separate stage. And using colloidal methods, we could control the size and the monodispersity of those particles very well. And in the second method, we were also able to control the size, oxidation state, and the loading of copper nanoparticles. There, with the advantage that we use a physical deposition method, which allowed us to prevent the use of ligand or organic molecule to limit the size of the particles. The second modification we made was to the cell configuration. In this case, we now feed CO2 in the gaseous state behind a porous carbon interface, a gas diffusion electrode, where we deposit our particles or catalyst. And this interface is in contact with the electrolyte, which can be recirculated or flown in a single pass through the cell. And if we recirculate it, we can also accumulate the liquid products that we make during a reaction and detect them better using HPLC at the end of the reaction. The gas the gas outlet is then measured using GC to detect ethylene, nitrogen, methane, and CO, of course. So if we go back again to the graph showing selectivity as a function of overpotential, and we look at the individual functionalities, then we can see that by changing the configuration of the cell, we were able to increase the selectivity of the individual functionalities, for example, in this case of the carrier, to about 100%, and also increase the current density or turnover frequency, the amount of product we made, significantly. These are much higher levels than we obtained in the solid-liquid configuration I showed you earlier. And also using a different synthesis method for copper nanocrystals, we were able to increase the selectivity to higher than 30% to ethylene. And using the sputtered one we made via physical deposition method, we were able to increase the selectivity to up to 55% and at high current densities. And this indicated the importance of the catalyst layer properties, for example, the hydrophobicity of the reaction interface between gas and liquid. If we go back to the bifunctional catalyst, here we mixed the colloidal nanocrystals with carbon black and with the nickel nitrogen doped carbon, and we mixed those with several ratios of nickel to copper and of carbon to copper to control the packing density of the particles on the support. And again, we measured the selectivity of that catalyst to ethylene, but also to the other products such as ethanol and 1-propanol that we were able to finally detect in the liquid phase because of the higher turnovers and the improved configuration. And what we saw is that the selectivity towards ethylene was modestly increased under certain conditions, but more importantly that we produced more ethanol and more 1-propanol, and this indicated there was some influence of the local CO we produced near the copper functionality that influenced the product distribution. And the same observation we had in a second case study where we looked at copper-silver nanocrystals, where silver is in fact the CO evolving functionality and the copper is the multi-carbon forming functionality. But in that case, we saw also an increase in oxygenates to hydrocarbons ratio, so the amount of ethanol, acetate, and 1-propanol versus methane and ethylene. But there it came at the expense of ethylene formation. And the reason there being that during reaction, those particles reconstruct and form copper-silver domains, which catalyze the pathway towards ethanol more selectively and disrupt, in fact, the pathway towards ethylene. So to study those changes, both in alloying, for example, of copper with nickel, or what happens with copper-silver nanocrystals after we polarize the electrode, and during reaction, we would have to sort to more in situ methods and mechanistic study of those catalysts to better understand their workings and to be able to optimize them. But also we have observed using the other synthesis methods for copper nanocrystals that catalyst layer properties are very important. And on the personal note, I would like to zoom out a bit of the bifunctional concept and look at other CO2, electrochemical CO2 reduction schemes, and how they can be combined with that concept, or if there is another research direction we should pursue. So I would like to thank my colleagues for participating in this research and helping me carry out experiments. And I would like to thank you very much for your attention.